the start of this WebEx Open Forum, we've got one of our graduates who joined us at the beginning of the year, Michael Dello, to give us a talk on what he did as his honours project, which was for geothermal research, but it is heat flow analysis and has application in petroleum. So I'll hand it over to you, Michael.
Thanks. Hi guys, so I'm talking about my honours project today, South Australian Heat Flow Anomaly, Source and Implications for Geothermal Energy. And I did this at the University of Adelaide with my supervisor, Derek Astrott. So what is heat flow? Surface heat flow is the flux of heat passing through the surface of the Earth. It's defined by this equation here, where Q, heat flow, is equal to K, the thermal conductivity of rock, which is a measure of how effectively heat is conducted through rock, multiplied by the temperature gradient, so that's the change in temperature over the change in depth. Now, heat flow here, it's defined by a combination of the radiogenic sourced heat flow and the basal sourced heat flow. So QB, the basal heat flow, that's just the heat flow flowing in through the base of the crust from the mantle. And QR, the radiogenic heat flow from decay of uranium, potassium and thorium. That is defined by this equation here, AD. So A is the amount of heat generation and D is the thickness of the crust. So if you have a relatively thick crust or a relatively high heat production, that's going to give you a high radiogenic heat flow. So my project involved looking at the South Australian Heat Flow Anomaly, or the SAFA. It's a Proterozoic terrain in South Australia. It's defined by these dashed lines here, extending further north into the Cooper Basin. So the mean heat flow in the SAFA is 92 plus or minus 10 milliwatts per metre squared. Compare this to a mean global Proterozoic heat flow of 49 to 54 milliwatts per metre squared. The SAFA is almost twice as hot as your average Proterozoic terrain, so it's really quite anomalous. Having said that, it's only defined by a relatively few number of points. The black dots on this figure here are the only heat flow measurements publicly available anyway in South Australia. So to start with, we took 5 new heat flow measurements in the Curnamona province and in the north in the Mount Painter province. Our new heat flow measurements are defined by the pluses. So we took measurements from Frome 8, 9, 12 and 13 and from Paralana 1B, which is the Petrotherm drill hole at the Paralana project. And the main purpose of my study was to try and determine the source of this elevated heat flow. In the literature, there's been debate around 2 possible sources for this, either an elevated deep mantle-based heat flow or an elevated shallow crustal radiogenic heat flow. So this is the heat flow across all of Australia. Again, you can see there's large areas where there haven't been any measurements whatsoever. So we're still learning what the picture of Australian heat flow looks like. So the SAFA down here, extending up into the Cooper Basin, where luckily we've got a lot of measurements, but there's just large areas where we don't have anything. So methods. We took temperature data provided by the Department of State Development and Petrotherm, and we made our own thermal conductivity measurements using optical thermal conductivity scanner, or a TCS, and that's just this apparatus on the right here. So we've put our drill core samples on top of this conveyor belt, surrounded on either side by standards of known thermal conductivity for calibration. And the way this device operates, we've got a temperature source here, and on either side we have 2 temperature sensors. So this apparatus will move along underneath the drill core. We have a temperature measurement taken before the core is heated. The core is then heated by a known heat source, and then we have a temperature measurement taken after the core has been heated. Now this track is moving along at a known speed and there's a known distance between the 2 temperature sensors. So the difference between the temperature measurements can be used to determine the rate at which heat is conducted through the rock. So we've got a profile of that here. The red's not quite showing up as well, but the red profile along the top there is the the temperature measurement taken after the heat source has been applied, blue before the heat source has been applied. So then the difference between those is used to get a thermal conductivity profile along the core. So we've got our two standards on either side and the sample in the middle there. Now, thermal conductivity is a function of temperature. So for almost all rock types, increasing temperature will give a decreasing thermal conductivity. So since we're taking our thermal conductivity measurements in lab conditions and not in situ conditions where the temperatures are obviously much higher, we have to correct for this temperature effect so that we can accurately measure the in situ heat flow. So there's a lot of models you can use to correct for this effect. I've taken the two most different models, the Chapman and the funnel model, to show you the max difference between the different models. So for two samples, arbitrary samples of 3 and 2 watts per meter per Kelvin, so you see with increasing temperature we have a decreasing thermal conductivity. There's actually quite a big difference depending on which model you take. We ended up using the Chapman model because it's been used in a lot of studies, it's been quite successful, but also because it doesn't require individual correction factors for different rock types. So whilst that makes our thermal conductivity measurements a little bit more generalised, it allowed us to measure a lot more samples and reduce our uncertainty per drill hole by just having more samples of measured for thermal conductivity. So here are some of our results. This is for the Paralana 1B drill hole. From left to right we've got the temperature versus depth, the temperature gradient versus depth, thermal conductivity and the heat flow. So for thermal conductivity and heat flow we've taken the mean for individual stratigraphic packages. The white measurements in the thermal conductivity plot with their respective error bars are the uncertainty for the heat flow measurements. So the thermal conductivity measurements before the temperature correction has been applied, and the red measurements are after the temperature correction has been applied. So you can see once the correction has been applied, the thermal conductivity has been reduced. This is the in situ thermal conductivity. And then we've taken the in situ thermal conductivity and taken the mean for each stratigraphic package. So that gives us the red bar for each stratigraphy, and the grey box gives us our uncertainty for that package. We've then taken the mean thermal gradient and the thermal conductivity for each stratigraphic package and given us the heat flow for each package. So in the region of the Konomoto province, this is the old data set before our new measurements, and then on the right we have our new data set. So relatively consistent with the existing data, but we've shown that high temperature, high heat flow actually extends further southeast, a little further southeast than previously thought. So there's 4 possible sources of heat flow, a heat flow anomaly. You can either have an error or systematic bias, effects due to shallow magmatic, hydrologic and tectonic activity. It can be due to shallow radiogenic source or to a deep mantle source. Now, previous studies have shown that the first 2 sources are quite unlikely in the SAFA. So I've focused my study on the last 2, the shallow radiogenic source and the deep mantle source. So I'll spend the next couple of slides trying to convince you what the source is. So in 2008, Reader proposed that the depth of a heat source can be determined by the lateral rate at which the heat flow changes. So if heat flow is changing rapidly over a lateral distance, then that indicates a shallow source. If it's changing slowly over a much greater distance, that indicates a much deeper source. So in the SAFA, from our new data points, we've determined that the heat flow in the Konomoto province varies from 128 to 84 milliwatts per metre squared over around 50 kilometres, and that's consistent with other places globally where heat flow is due to a shallow radiogenic source. That's actually quite a rapid change in heat flow over a short lateral distance. Here we've got the P-wave seismic velocity at 150 kilometres depth from Rawlinson et al. 2014. So in the southeast of Australia, especially around Tasmania, where we have elevated heat flow due to a deep mantle source, we've got relatively slow seismic velocities. compared to in the Safa and especially in the Konamoto province, we've got quite high seismic velocities, 150 kilometres depth. So this is what you'd expect if you had a shallow source. If you had a deep source, you'd expect much slower temperatures. So in the Safa we have a relatively thick, cool and dense lithosphere, indicating primarily a shallow source. And finally, we've modelled 3 geotherms based on the method of Hasselrock and Chapman 2011 to show the effect of varying surface heat flow and heat production on the lithospheric thickness. So geotherm 1, we've taken a relatively average Proterozoic heat flow of 40 milliwatts per metre squared and given it a relatively average crustal heat production of 0.65 microwatts per metre cubed. We've taken the Mantu adiabat to represent the point at the intersection of the geotherm with the Mantu adiabat to represent the lithospheric thickness. So geotherm 1 plots the lithospheric thickness of about 195 kilometres. That's quite consistent with a measured mean Proterozoic thickness, lithospheric thickness of about 200 kilometres. Now geotherm 2, we've plugged in the mean heat flow for the South Australian heat flow anomaly, 92 milliwatts per metre squared. And we've given it a slightly higher but still relatively low heat production of 1.495 microwatts per metre cubed. Now you can see here QB, which is the basal heat flow, is quite high, so that's the main component for this geotherm. It's 81.6 milliwatts per metre squared. Now geotherm 2 only plots the lithospheric thickness of about 45 kilometres. Seismic data over the South Australian heat flow anomaly shows that its lithospheric thickness it's still a little uncertain, but it's within the range of 150 to 200 kilometres thick. So 45 kilometres is well outside that range. Finally, we've got geotherm 3, again plotting with the mean heat flow of the South Australian heat flow anomaly. But this time we've taken the mean heat generation from the Newman 2000 study, which took several thousand samples of measurements of heat generation across the crust in the South Australian heat flow anomaly. We've plugged that into our heat generation, 4.14 microwatts per metre cubed, and this geotherm plots with a lithospheric thickness of about 195 kilometres. So that's within our range of measured lithospheric thickness of 150 to 200 kilometres thick. So from these 3 sources of evidence indicating a shallow crustal, primarily a shallow crustal anomaly, we've concluded that that is the main source of heat flow. So there's a lot of projects, pilot plants and small projects in the Safa at the moment trying to develop geothermal energy. So you need 3 things for a geothermal project to be economic. You need high temperatures at shallow depths, you need a high presence of fluids and high permeability. Now, if you don't have the high temperatures at shallow depths, then you're not going to be able to reach your resource at economically drillable depths. But your high presence of fluids and high permeability can be stimulated through hydraulic fracturing and pressure stimulation. So here's an example of an unconventional geothermal power plant, such as the resource we have in South Australia. So you drill 2 holes, pump cold water down one hole. That's heated up by the hot rock. It's then pumped back up the other drill hole. It's run past a heat exchanger, which turns a turbine, generating energy. And as it's a closed loop system, the water is cooled and pumped back down to the ground. Now the hot rocks in the South Australian heat flow anomaly are granites, because granites have high uranium, thorium, potassium heat generation. The problem with granites is they don't have high permeability or presence of fluids. But luckily in the South Australian heat flow anomaly, the granites are pre-fractured and the fractures have been closed using mineral precipitate. So it turns out these are actually quite easy to refracture and reopen and to keep open. So some people have been working on that, looking to fracture the granites. Or you can do what Petrotherm is doing. They're actually drilling into the sedimentary rock just above the granite. So whilst not quite as hot, much easier to to fracture and to get fluid flow, so improves your resource that way. Now, depending on the type of power plant you're using, you need temperatures of about 60 to 200 degrees Celsius. So in the Konomoto province, we have 60 degrees Celsius at around 810 metres depth and 200 degrees Celsius at 6.5 kilometres. Now, 6.5 kilometres is too deep to be drilling economically, but 810 metres is very shallow, so very easy to develop that geothermal resource. And in the Mount Painter province, it's even hotter, so we've got 50 degrees Celsius at about 565 metres and 200 degrees Celsius at 4.4 kilometres. Again, 4.4 kilometres, still a bit deep to be drilling economically, but at 565 metres it's very shallow to get a temperature that's economic to be drilling for a geothermal plant. Now, geothermal projects have been a bit dead in the water in South Australia at the moment. There's a few pilot plants. There's the pilot plant at Inaminka, but it's not really going anywhere at the moment. The main problem is the distance from the energy source to the energy market. If this was a couple hundred kilometres closer to Adelaide, I think we would have already developed it. But I think through a combination of supplying power to the countless nearby mines and petroleum projects, I think that this resource can really take off. Okay, so it's all well and good, but we're a petroleum company, so why should we even care about heat flow? Well, there's implications for the depth of your hydrocarbon kitchen, for basin history and modelling, and actually the temperature of your reservoir can affect your CO2 content. So this was beyond the scope of the study, but I'd like to see the heat flow plotted against the CO2 content of reservoirs to see if we can find a correlation, and then maybe to estimate CO2 content before we actually drill a reservoir. So in conclusion, we've conclusively determined the SAFA is primarily a shallow crustal radiogenic source. We've shown significant geothermal potential in the area. The average heat flow in the Konomoto province is 99 milliwatts per metre squared. That's extremely high for a Proterozoic terrain. And whilst we've expanded the heat flow database, there's still huge areas across Australia where we have just no idea what the heat flow looks like. So future work should aim to expand the heat flow database, especially in areas where when you have low heat flow, no one wants to drill there, so you get less measurements in those areas. So I think less attractive, but we should be sinking a few drill holes into areas, not we as Santos, but in general we should be sinking drill holes into areas with low heat flow to try and build up a picture, because you never know, we might find another anomaly there. So I'd like to thank my supervisor Derek Hasterock, co-supervisors Bettina Bendel and Martin Hand, co-workers Alex Muss and Henry Johnson, thanks to the University of Adelaide Department of State Development, and thanks to my scholarship providers. Thanks everyone. Any questions?